Good morning, everyone. Welcome to the second day of European Lisp Symposium. And the first talk of our first session today by Stefan Monnier. It is about opening the closures and looking into inner object of lambda. Stefan, please.
You can hear me? Okay. Oh, doesn't. This one seems to work. Better? Good, okay. So I'll be talking about basically how to make functions bigger. That works. Okay, so basically this is, in a sense, it's how to bring functions or closures up to being objects in some way. So it's really, sorry? Exactly. So aren't functions already objects? Isn't objects and closures basically the same, right? So that doesn't make much sense. Yet in practice, if you look at existing scheme systems, they don't seem to be quite satisfied with their functions. There's all kinds of slight extensions like, fun callable objects or procedure properties. And in Scheme, they have those tagged procedures and, there's always something. It even goes back to Lisp machine Lisp. It's not lazy ML that I have here, where they had those things called closures and entities. They had dynamic scoping back then, so closures didn't mean quite the same, but more or less. And of course, in Emacs Lisp, we have docstrings and interactive specs as well, which are things you can look from outside. It's not quite normal functions or properties of normal functions. So we can, grow functions, and we know where it goes, right? It leads to those kinds of monsters. And I want something a bit leaner. So I want it bigger, but not quite so big. I want just a structure and a function together, but I want to keep it cheap. So just to give you the outline of the talk, I'm first going to show the motivating example, then briefly basically re-mention the solutions we already saw, and then show a kind of theoretical account of what open closures are, which I call the open lambda calculus, along with the implementation of the theory from the theoretical point of view, to kind of motivate why this makes sense. And then I talk about how I do it in Emacs, since this was all done in Emacs Lisp. Just to give some context, this is a slide from a talk I gave about 2 years ago in a very different context, but nevertheless, the point is that in that talk, I was showing how to take algebraic data types, which in statically typed languages, functional languages we love, but they're kind of big. They do everything, from sum types, product types, and blah, blah, blah. And so I wanted to reduce this down to individual elements you can compose together to get back those features. I like to have things that are nice and separate. And here I'm just taking structures and functions and kind of mushing them together. So I'm not sure exactly in which category I have to put this presentation. I think I feel fairly hypocritical in this respect. But you'll see there's some kind of rationalization for why I like it anyway. Okay, so here's the motivating example. So if you use Emacs, you might have heard of advice. And this is basically what is behind advice. So say you have a function stored somewhere typically in a variable, and you want to be able to change it, modify it somehow, by just adding functionality to it. So you have this add function, and it takes 2 arguments. A function you want to add, actually 2 plus 1, there's always this off by 1. So you have first a function you want to add, the variable to which you want to add this function, and the way in which you want to combine the two, which I call where. You can execute fun before the original function, or after the original function, or around the original function. You get the idea. So how do you do that? You basically call this compose function, which takes two functions and composes them, right? So the two functions are fun and list fun. I call the other one list fun because as you add more function, you get a kind of structure where you have a list of functions internally, even though it's always just a function, but there's a kind of internal structure which looks like a bit of a list. So here's how you do it with closures. It's quite easy. You just use a wrapper like a lambda with a rest argument that takes everything and just applies the two subfunctions in some way, or calls the two subfunctions using apply. Does it make sense? Okay. So problem solved. We know how to do that. You can do a def var for a function that calls A that just executes A originally. Then you can add function B to it, add function C to it, and there you go. You have a function that calls A, then B, then C. Okay. Thank you for any questions? Okay, I just forgot one little detail. What if you want to remove functions? Now, suddenly you're in trouble. Adding function was fine, but removing function is a little more delicate. How do you uncompose a function? You take this list fun, which internally has some kind of list structure, but all you have is a function. You don't really know what that function is. It might even not have this list-like structure. It might just be the original function. You can't tell the difference. So you would need to look inside. And functions are opaque, right? So you don't really have that option. So what are the existing solutions? Well, in Emacs for advice, since at least in Emacs 24, we use the first solution. We just look under the hood. It's nice. You get your hands really dirty, and it works. So why not? But it's not quite satisfactory. So there are a few other options, like using a special calling convention, and then you have to be careful to make sure that it always works. Or you can use fun callable objects or any of those other solutions I mentioned. And all of those other solutions I mentioned, like fun callable objects and procedure properties, they give you just enough rope that you can hang yourself if you want to in the way you want to. But they don't give it enough so that you can do it conveniently. It's always like, yeah, you can do it, but you have to use a kind of duplicate information somewhere, or there's some overheads when you call the function, or something like this. It's not really satisfactory. Of course, JavaScript and Python, they have that down. It works really well. It's a bit over the top, but and if we had objects, of course, that would also be an option. But we wouldn't want that. It's redundant. So clearly, there aren't enough solutions. We need more. So the solution I have is based on this idea of the open lambda calculus. So here at the top, you see the syntax in BNF. So it can be, it's really just a very minimal calculus, basically the same as the lambda calculus with just one extra construct and the lambda being modified a little bit. So you have constant C, you have variables X, you have the OAP, which is the function call, and with just one argument. I kept things simple here. And you have the oref, which is basically the access to a slot in a structure. But instead of having a constructor for lambda and a constructor for structures, I have a single constructor that plays both roles. So my olam takes an argument xa and a body eb. That's your function, the function part of this open lambda. And this xe with an arrow on top is basically a sequence of bindings, as kind of let bindings. And so this gives you the various slots you want to expose as if it were a structure. So the dynamic semantics are very straightforward. The second line is the first one to read. It's when you want to access one of those open lambdas as if it was a structure. So you have an oref on one of these open lambda, and you want to select the field number, the slot number I, and it just selects the value vi from the bindings, the xv with an arrow on top. So this is just a regular structure access. And if you want to call the function, then those extra bindings are mostly ignored, but not completely, you'll see. You just have your actual argument va, which you substitute wherever these, the formal argument xa occurs. So you see, you execute the body where xa is replaced by va, but you also do the substitution of the fields. So everywhere where the variable x from one of the fields occurs, you actually use the value corresponding to it. So it's, you actually get to see the fields of the structure from the body of the function. And of course, if you want to have your good old lambda, it's just an O lambda with an empty list of fields. So it's a strict superset in the sense of the lambda calculus. Wrong key. Okay, I know you like typing rules here, so I figured I couldn't resist and present a bit of some kind of typing system for this language. You don't have to use a typing system, obviously, and the main point is just to show that the typing rules, you can come up with typing rules for this system in a very natural way, and they look absolutely normal. They look exactly like the usual typing rules. One side being the typing rules for tuples, the other side being the typing rules for function calls. I put the types in red, so it's the dangerous part to avoid. But the important part is this OARW, which stands supposedly for open arrows, but you can pronounce it like wow. So it basically takes 3 arguments. The last 2 are basically the type of the incoming argument, the type of the return value, and the tau with an arrow is basically the type of each of the fields, or each of the slots of your open closure. So basically of your tuple, if you look at it as a tuple. And again, if you look at the typing rules for OAP and OAP and OREF, sorry, then you'll see that they basically correspond to the usual typing rules for function calls and the usual typing rule for record selection. You can actually use dependent types if you like it, like I do, but here I kept things simple. So the main point here is just to say that this is very straightforward. It's the same old rule as usual. There's nothing strange going on, which is satisfactory. It means that we are on unknown territory. There's everything's working well. Okay, so now that you've seen this, I want to refresh a bit your memory about how closure conversion works. Why do I want to do this? It's because in terms of why do we want to use open closures, why does it make sense to do this? I think you need to look at it as how do you actually compile it? How is this going to work? So closure conversion is taking functions in your original code and basically turning them into tuples so that you have code that is completely closed on the one side and data which keeps the captured variables and those kinds of things. So the important part is the second line. The first important part of is the second line. So you do the closure conversion of a function call. What does it turn into? Well, it turns into, evaluate the function down to a value which you bind to x. And then you want to call this function, but it's not a function anymore. After closure conversion, it's turned into a tuple that has as typically the first field points to the actual codes, and then the other fields contain the free variables. So you end up calling the ref x0, so that's extracting the first field of your tuple to get the actual codes. So you call these codes and you pass to it x, which is the closure, so that the code can actually extract the information from the closure where it needs to refer to free variables, and then you pass the original argument. So this is this should be something you've seen sometime, probably maybe a long time ago, but something you might be familiar with. The second part is how you do the actual creation of those tuples. So when you compile a lam or lambda, you have to look at what are the free variables of this lambda. This is what the fv call does. So you look at the free variables of the body eb, to which you have to eliminate, of course, the argument xa. And those free variables turn into the things you want to capture. And so you will return a tuple made up of the codes corresponding to eb and the free variables y1 to ym, which you need to translate with a sigma, but these details don't really matter here. So just the general idea is this, that you take your functions, you turn them into tuples. So that might give you the idea of why do I want to do open closures? Is that my closures turn into tuple anyway. So why not use some of those fields as the fields of a tuple? And that's exactly what happens when you do closure conversion for open closures. So here I use red not for types, but for the things that are interesting rather than dangerous. And so here you see the algorithm is exactly the same as before. It's just that now you have those extra fields which you plug directly in your tuple as typically the first few fields of your tuple. So you can indeed access your fields in the normal way. And if you don't have any extra fields, like we use simulating lambda with your open lambda, you get exactly the same thing as before. So there's absolutely no overhead involved with it. Okay? All right, so that was the theory. Now, what does it look like in Emacs? So the theory is trying to be minimal and have a kind of nice meta-theoretical properties, so it all makes sense. But in practice, you want to have something slightly more flexible and prettier, maybe. So we made some changes compared to the theory. The first change is that when we have an open lambda, which we call O-closure lambda, we have an extra, instead of just a list of slots, we have an extra information, which is a type associated with this lambda. So we want to give some kind of typing information where we might want to be able to have some kind of hierarchy of types. Or actually, not necessarily a hierarchy. It can be a directed graph, but anyway. So that's my O-closure lambda. Also, of course, I have any number of arguments, as you can imagine. And since we have this notion of type, we need some way to define new types, which is what this O-closure define does. O-closure define creates a new O-closure type, and it works in a very similar way currently to def struct, actually a mix of def struct and def class, but the syntax is more taken from def struct. So the O-closure define says, here's the name of the type, then you have some number of slots, and that's basically what you would expect from those things. And then you have a function like O-closure type to extract the type from an O-closure. And of course, you can use this type to dispatch with def methods and those kinds of things. Just one detail, slots are read-only by default. This is quite unusual for Emacs. Not unusual for me since I work in mostly pure languages. So that's probably the reason. But there's a technical reason behind this, is that mutable slots are more expensive, significantly more expensive. You need to allocate in the context of Emacs. We could implement it a bit more efficiently in some cases with some extra work, but we don't bother. So every mutable slot incurs an additional cost of basically creating a const cell that contains the actual value. So then an additional indirection. So they work fine, but it takes more work and it costs more, so you have to ask for it explicitly. Okay, so now that we have open closures, how do we actually solve the original problem, right? We had this problem with advice, remember? So now we need to redefine compose function because we used to define functions, used to do this composition using plain lambda, which is still opaque. We haven't changed lambda. It has the same semantics as before. So now we have to use open closures. So this O-closure lambda at the top, you see now basically the red part is what was changed. So we actually tell them what type it is. It's type advice, which must have been defined before, but I didn't show you this part. And when I defined the advice, I said that it had 3 fields, a field car, a field CUDA, and a field where. And as I said, it has a kind of list structure, so car and CUDA actually make a lot of sense here. And I just have to say, the car will contain the actual function, the CUDA will contain the rest of the function, the original value of the function, and I also have to remember the where, which I used to not need to do that, but now this is a kind of extra slot in the closures. So my closures will be slightly more costly than before, but that's because I need to be able to do the remove, and not because O closures force me to do it. And notice in the body of the function, I don't call car and CUDA, I don't call fun and list fun anymore. Instead, I call car and CUDA. So I refer to the fields of my open closure from the body, And I could call fun and list fun just as well. That would also work. But now that would mean that I basically have two copies of the same information, once as slots and once as opaque or hidden captured variables. So there would be no point there. And you'll see there's actually an even more interesting use case. So now how do we remove an advice? Well, there's no magic anymore, no need for any magic. We can just look at the slots. So we start by checking the type, making sure that this function is indeed an advice, that is a composition of two functions which result in those kind of advice composites. So I check that it's an advice. If it's not an advice, then I'm basically at the end of the list, so there's nothing to remove. And if it is an advice, then I know that I have a car and a CUDA and a where field, so I can extract those with slot value simply. And then if my car slot is the function I'm trying to remove, then everything is done. I can just return the CUDA, which is the rest of the function. And if not, then I remove it from the rest of the list and recompose the result. Okay, and that's where I need this where field. I need to remember this where field so that I can recompose the result once I remove one of the function. All right, one final detail. I actually added an extra functionality, which is functional update. So as I said, slots are read-only by default, but you can actually modify them as you create a new copy. So you can ask to have functional update functions with this colon copier property on the type definition. So here, this would define a function advice with CUDA, which takes an advice O-closure and a new value for the CUDA. And so it returns a copy of the original function with the CUDA field being modified to the new value. And that's where it's important here to refer to car and CUDA when we call the functions instead of referring to the external variables. Because when we modify the fields, then suddenly my apply car and apply CUDA end up calling this new value when I make the functional update. And so I can now redefine my uncomposed function in a slightly different way here by using advice with CUDA. Instead of basically recomposing manually by calling compose, which will again check where and decide which one of the variants we should use, I just copy the function that I already had and change the CUDA. So I can call advice with CUDA, pass it the original list fun, and it will just change the CUDA field, which is slightly more efficient. It saves me from having to consult the where field, so I don't even need to store the where field anymore. Of course, in practice, I still do because when I print the function, I still want to see the where field. But in theory, at least, we could get exactly the same efficiency as before in terms of memory use. Okay, so just for reference, this was the old code before. So there's no big difference. It's not a killer feature, but it's a nice feature to have. Okay, I think I'm going to skip this detail. Just mention, where open closures are used. It's not very common to need them. Just like it's not very common to use, fun callable functions and those kinds of things. Sometimes you need them, and when you need them, it's really convenient to have them. But most of the time, you just use your good old lambda. And we love it because it's very handy in all kinds of places. But still, I did find various uses for it. Other than the advice, of course, I use it for next method P, where we need to decide, is the next method really a next method, or is it going to signal an error? Or apparently in some implementation, just do nothing. And so instead of having to figure this out via some extra side information, I can just check the type of this function. Is this a real next method, or is it the special one that just does nothing or that signals an error? Also use it in Emacs for keyboard macros, which used to be defined as a lambda, which there was some special calling protocol to extract information from inside, where the inside information was a tuple of 3 values. Now I just mush the two together, and it's cleaner and simpler. Efficiency doesn't really matter at this point, but it was a nice improvement just in the code. And I managed to use it for various other things. We could actually redefine the notion of command in Emacs with this, since command is basically keeps some kind of interactive spec. And same thing for doc strings. We could also use it for auto-loaded functions. Currently, we don't actually do that. I mean, I have code that does it just to make sure that it does work. But for all kinds of historical and also efficiency reasons, closures are not implemented in a very satisfactory way. I don't currently intend to actually use that in real Emacs. Okay, so in conclusion, I propose open closures, which are significantly more involved than the kind of minimalist extensions that are usually proposed in apply hooks or functionable objects or something like this. It's a bit more involved. It's a bit more far-reaching in a sense, but it's still a very simple extension with no cost in terms of performance. And I think it's a neat part of it. It's also, from a theoretical point of view, it's very straightforward and clean. And in practice, it cleans up various ugly hacks. Most of them were due to yours truly. And it also makes it easy to extend and clean up a few things, mostly for pre-printing. You can pre-print various functions in special ways. And I think that's it for today. Thank you very much.
Thank you, Stefan. So are there questions?
Thanks. I might have missed slide number 18, please, if you could go back. Maybe I missed a detail here because
here
you had a lot to say about, yes.
Yes.
What's going on with apply car CUDA args right in the middle?
Yes. So this used to be apply fun, list fun, okay? But now fun and list fun are available as the car and CUDA field. So I just reuse the field value directly. Okay, and it's important when we do the functional updates so that when you change the field, it also changes the behavior of the code.
Yeah. If I may, on your typing slide, I don't remember the number, but you typed everything except your index. Your index, I guess, is just a natural, but is that all there is to it?
Oh, yeah, it's just an integer.
Can it be something else?
No, currently not. Yes.
Sorry?
Conceptually,
can it be something else?
Well, conceptually, we could use names. In Emacs Lisp, we actually, the slot value takes the name of the field instead. But for the meta theory, it's much simpler if I just use an index instead of name.
So could you go into more detail about the actual memory representation or the performance characteristics of how closures are implemented in Emacs Lisp right now? Like, are you using flat closures? Are they just like literally code pointers paired with like a flat environment object? Or
yeah, it's kind of embarrassing to go into the details. No, actually, closures in Emacs Lisp, they're represented as basically two parts. One part is a kind of object with 4 or 5 fields, which has the arg list, the actual bytecodes, a pointer to a string, which is the bytecodes, then a pointer to a vector, which contains the constants used in the codes, and then another one which has like the stack depth and the maximum stack depth or something like this. And for closures, we actually keep the extra information, the captured variables, as if they were part of the constant pool. So they're part of the inner vector. So when we create a new closure, we have to create a new copy of this constant vector, which means we copy not just the actual captured variables, but also all the constants that go with it, which is rather costly in some cases. And on top of that, we need to copy the overall 4 or 5 field objects that holds it all together. So it's far from being the most efficient representation. In a sense, it is a flat closure in that we do just keep the captured variables in consecutively in a vector, but it's much less efficient than that currently.
thanks.
You mentioned multiple inheritance and that you can define custom types. So is there something like redefine O-closure for updated type or something? Or can we expect something like that?
I'm waiting for a patch. There's some Marco something guy. He said he was going to work on that.
You mentioned there were 3 or 4 types of advice, before, after, and something, I don't remember, instead of. The instead of has to have some sort of continuation, right? How do you handle the continuation in this wrapping and
So,
unwrapping?
so here I mentioned the override. There are a few others. There's like you can filter arguments only or filter the return value as well. You can imagine other ways to compose functions, basically. So the override one is somewhat special because if you look at the way you would implement it when you compose, you completely forget the original function because you completely override. You just replace the old function with the new one. Well, you don't have anything to continue afterwards, so there's no need for any continuation. So in this version, it's really efficient, but then you can't remove. You can't remove fun because you can't remember what was the old one. So in the actual implementation, even in the past, in Emacs Lisp, in the case of override, we actually do use a wrapper function that calls fun, and that keeps a reference to the original list fun so that we can recover it later, but it doesn't actually use it. It doesn't call it. No. So you can end up calling it if you remove the override advice, and then the list fun reappears at this point. But yeah, does that make sense?
Okay, thanks again to Stefan.
Thank you very much.